Es para mí un verdadero placer y un honor presentar al profesor Stachel, a quien conozco desde hace ya muchos años, 26, desde otro año marcado, otro año einsteiniano, 1979, cuando se celebró el centenario del nacimiento de Einstein, un año que yo pasé en Filadelfia junto a Peter Havas, un gran amigo de John. Recuerdo, por ejemplo, que aquel año se celebró en el Instituto de Estudio Avanzado de Princeton una gran reunión como esta para celebrar, honrar y estudiar la memoria de Einstein. John Stachel, entonces recuerdo, me enseñó, es la memorabilia, me enseñó el despacho que había ocupado Einstein. Recuerdo también, es mi cuota de einsteiniana, en un coche, un corto trayecto con John, Peter Havas, Adolf Grunbaum y Helen Dukas, la secretaria de Einstein. También en aquella ocasión, es otro de mis más queridos recuerdos, pude escuchar la única vez en mi vida a uno de mis grandes héroes científicos, Paul Dirac. John Stachel estudió en el Stevens Institute of Technology. Su tesis doctoral data de 1962. El título de ella es La derivada de Lie y el problema de Cauchy en la relatividad, en la teoría general de la relatividad. Pronto fue profesor auxiliar en Lehigh University, en Pensilvania, donde estuvo hasta 1961, después en la Universidad de Pittsburgh, también en Pensilvania, y finalmente a partir de 1964 en la Universidad de Boston, que ha sido su hogar intelectual desde entonces. Pronto fue full professor, en la actualidad es profesor emérito y también en la actualidad es director del Centro de Estudios Einsteinianos de esa universidad. Su primer artículo apareció en 1966 en el campo de la relatividad, de la teoría de la relatividad general. John Stachel se mueve en muy diversos campos. Son muy numerosos a lo largo de su carrera científica esos trabajos dedicados a la relatividad general sobre cuestiones como soluciones exactas, el problema de Cauchy, formalismo lagrangiano, estructura conforme, también en ámbitos como la teoría de la relatividad especial, dinámica relativista. También ha dedicado, a partir precisamente de 1979, una parte muy importante de su carrera al campo de la historia de la ciencia, en particular a esos estudios einsteinianos. Aquel año, en 1979, apareció, por lo que yo sé, su primer artículo, su primera publicación dedicada a Einstein. Muy apropiadamente, por algo que ustedes verán enseguida, estaba dedicado a Einstein and Civil Liberty, Einstein y las libertades civiles. Luego, a lo largo de los años, vendrían muchos otros trabajos dedicados a Einstein y el problema del disco que gira, Einstein y Michelson, la génesis de la relatividad general, Eddington y Einstein, Einstein y los cuantos, Einstein y Bose, la polémica entre Hilbert y Einstein, lentes gravitacionales, etcétera, etcétera. Algunos de estos artículos, los mejores sin duda alguna, están recogidos en un libro que yo les recomiendo, publicado por Birkhauser en 2002, Einstein from B to Z, Einstein de la A, B a la Z. Ha sido editor de numerosos libros, es decir, responsable, director. Mis favoritos son el dedicado a Dirk Struik, otro a Leo Rosenfeld y también el que dedicó precisamente a los 5 artículos que Einstein publicó en 1905. Se titula Einstein, el año milagroso, apareció en 1998, está publicado, traducido a numerosos idiomas, entre ellos el español. Pero en el ámbito de los estudios einsteinianos, el nombre de John Stachel estará eternamente no va a estar nada eternamente, pero desde luego permanentemente, mientras el tema de los estudios, el tema del estudio de Einstein constituya interese a alguien, estará ligado a los Collected Papers of Albert Einstein. Los dos primeros volúmenes, aparecido el primero en 1987 y el segundo en 1990, fueron dirigidos, el editor, por John Stachel, que más que ninguna otra persona, es una larga y no siempre feliz historia, luchó porque se pusiese en marcha el proyecto, luchó, por ejemplo, frente a algunos de los albaceas, de los depositarios del legado de Einstein, porque el proyecto de una edición de todos los escritos de Einstein se pusiese en marcha. Y vaya que sí se puso. Los dos primeros volúmenes, como digo, fueron editados por él, estableciendo unas normas, unos criterios de excelencia, por ejemplo, en las notas editoriales, que tengo la tristeza de decir que no siempre han sido seguidos, no son seguidos en la actualidad. No puedo imaginar en el futuro por ejemplo, biografía de Einstein que no lleve en el índice onomástico el nombre de John Stachel como editor de esas fuentes indispensables para la ciencia, para la Biblia, para los estudios einsteinianos. Pero todo lo que he dicho hasta ahora está bien, es propio de un currículum universitario, de un currículum académico, pero con eso ustedes no podrían comprender o entender y finalmente admirar la personalidad de John Stachel, que es mucho más rica que todo esto. Como en esta sala hay muchos jóvenes, yo les voy a leer en 2 minutos unos párrafos de lo que él ha llamado autobiographical reflections, reflexiones autobiográficas, que han aparecido no hace mucho en un libro, en un first read que algunos de sus amigos editaron con ocasión de sus 70 cumpleaños. En estas citas verán ustedes la humanidad, el compromiso con su mundo y con su tiempo de John Stachel, que por muy diversas razones, por familia, por donde nació, por el tiempo que le ha tocado vivir, se ha tenido que enfrentar, relacionarse con algunos de los problemas, de las situaciones más marcadas, más características, incluso más dramáticas de nuestro tiempo. Es John Stachel el que escribe ahora. Crecí en una sociedad predominantemente cristiana, un judío no religioso sin lazos con la comunidad organizada judía. Las raíces de mi familia en la cultura yiddish del este de Europa, por una parte, y el civilizado, entre comillas, antisemitismo de mi patria, por otra, y sobre todo las bárbaras formas que adoptó el antisemitismo en Alemania mientras yo crecía y que culminaron en el Holocausto, no me dejaron dudas sobre mi identidad judía. Sin embargo, estas son unas palabras que le honran, mi orgullo por los logros de mi pueblo al sobrevivir y superar el criminal asalto a su propia existencia se ve atemperado por la experiencia de ver cómo las víctimas de la opresión se han convertido ellas mismas en opresores de otras personas. Hasta que el pueblo palestino no haya logrado su liberación, no puedo pensar acerca del Estado de Israel sin emociones encontradas. Y hay la segunda y última de estas citas de esa autobiografía, esas reflexiones autobiográficas de John, es la siguiente. Y que ayudan a comprender, por ejemplo, que si ustedes miran su bibliografía, se encuentren no solo con trabajos como los que he citado hasta ahora, sino como otros titulados, pues el concepto crítico marxista de la ciencia, 1994, Marx, ciencia y capitalismo, de 1998. Crecí en una familia comunista en el corazón del capitalismo. Fue durante la década de los años 30, cuando el capitalismo americano estaba sufriendo su crisis más profunda, hasta el momento, y el Partido Comunista Americano era más fuerte. La Unión Soviética todavía representaba las esperanzas de mucha gente en todo el mundo, incluyendo algunos en Estados Unidos. esperanzas de una transformación socialista de la sociedad. Mi padre fue un líder del Partido Comunista Americano, que sufrió prisión por sus creencias durante la era de McCarthy. Durante muchos años fui un comunista dogmático, pero como sucedió a todos en el movimiento, a tantos en el movimiento comunista, en un momento determinado, en mi caso la invasión soviética de Hungría en 1956, tuve que reexaminar mis puntos de vista. Terminé comprendiendo que el problema con el Partido Comunista no era el de que estaba demasiado a la izquierda, sino que estaba demasiado lejos en el este. Esto es, independientemente de que defendiese muchas buenas causas en Estados Unidos, que se convirtió en un siervo de los intereses rusos que no tenían nada que ver con la causa del socialismo. Esta es la persona que les va a hablar a continuación, un hombre al que, en esa frase hecha, nada del humano le es ajeno.
Gracias, José Manuel, por estas palabras tan sincero, tan emocionante para mí. I will now switch to English, unfortunately, but as far as my talk goes, most of it will be projected on the screen. So if you can read English, it doesn't really matter whether you can understand my words. As the last speaker today, and as one of the foreign guests here, I think it is incumbent upon me to thank profoundly not only the organizers of this splendid conference, but the staff of the Congress who did so much to make our stay here so pleasant, so enjoyable, so fruitful. I think all of the foreign guests here will join me in a round of applause for both the organizers and the staff of this Congress. Now a word as to my point of view. For a number of years I've been preaching that the unit should be the problem, not the discipline. I think this is very important, especially for young people embarking upon a career in research. The important thing is early in your career to define some problem that you want to work on, and then look upon disciplines as tools that you use in the course of solving a problem. Do not let disciplinary boundaries determine the boundaries of your thought. Look upon the various disciplines as tools. When you ask someone what he or she does, they don't say, I use hammers, I use saws, I use planes. They say, I build houses. And in the course of building houses, I use hammers, I use saws, I use planes, I use whatever I need to get the job done. And the background today, for my talk today is the problem with which I have been concerning myself for the last few years, the problem of quantum gravity. And in the course of that problem, as you will see from my talk, I have employed disciplines such as physics, history, mathematics, philosophy. I will allude to all of these today. In mathematics, I will try to confine myself to concepts and not formulas, so there won't be many formulas in the talk, but there will be a number of mathematical concepts. Space and time are intimately related, and it's been known since ancient times. Kinematics, the description of motion, must involve both. But the modern concept of a union of the two in one abstract space only developed fully in the 20th century. And in the first historical critical section, I use the word historical critical in tribute to Ernst Mach, who's been mentioned earlier, I shall discuss Galileo-Newtonian space-time and Minkowski space-time, the space-times of pre-special relativistic and of special relativistic physics, respectively, both of which neglect the influence of gravitation, and both what has been called general non-relativistic and general relativistic spacetimes, the family of spacetimes which include the effects of gravitation on spacetime. And we can understand the relationship between these by using what I call the Bronstein cube. Where the name Bronstein comes from, you will see later on. It's a tribute to a Soviet physicist who perished in the Stalinist purges of the 1930s. If we start from, let's see, this works. How does this, is this a projector? Let me show you how this works.
Just press this.
Press this. Oh. Okay, thank you. If we start from Galileo-Newtonian theory, you can go in several dimensional directions. You can go in the direction of c, or 1 over c, since we want 1 over c to be 0 at Galilean-Newtonian theory. You can go in the direction of g, the Newtonian gravitational constant. You go in the direction of h, the Planck's quantum of action, and you get the various theories. You can go from the c direction, get special relativity. You can go in the h direction and get non-relativistic quantum mechanics, and so forth. We'll say a little bit more about this diagram later on. But this gives us a way of situating ourselves in the historical development of the theories using these 3 parameters, 1 over c, h, and g, as our coordinates, so to speak, for this picture. I'm going to briefly go through a lot of history because I want us to understand that when we do such a simple thing as do a space-time diagram, we're really taking the fruits of thousands of years of human endeavor and some remarkable conceptual achievements, and I'll try to very briefly indicate the course of those achievements. The representation of a time interval by a length, something which we take for granted when we do our space-time diagrams, is an example of what has been called the spatial representation of time by Henri Bergson, or the spatialization of time by Émile Meillarson. And it was the culmination of several preceding developments, which I shall briefly review. Here's the most beautiful slide I think I have. It's a cave painting, as you may have gathered. And I want to draw your attention to the fact that one sees here absolutely straight lines. You see, the human figure is a stick figure, not very important. The important figure is the wounded bison here. But even the stick figure you see is enclosed with straight lines. We have this sort of a totemic bird-like figure on a straight line. We have the arrows that are straight. You see transpiercing the bison and some other straight arrows down here. When you think about this, it's a remarkable achievement. This means that not only had the concept of straightness in space been recognized, but the idea of representing straightness in space in a figure was already as old as the cave paintings. Now, the earliest preserved graphical representations are at most 40,000 years old, not because the ideas may not have been older, but because older cave paintings would have deteriorated by now. So all we can say is this sets a lower bound for the time when the concept of representing a straight line in space by a straight line in a diagram arose. Implicit in such drawings, especially insofar as they are realistic, as this cave painting, is the representation of the spatial dimensions of an object by lines in the drawing. Or as we may say, the representation of spatial dimensions in reality by lines in a drawing, which I want to emphasize is already a manifestation of a considerable power of abstraction. The next step is shown in this Babylonian cuneiform tablet. The question of an even more abstract representation, that of a non-length by a length. Again, something we take for granted. Every day we look in our newspapers and see drawings of price changes, price of oil, how it varies with time and so forth. We're quite used to seeing representations of non-lengths in a diagram by lengths, but I want to point out there's a remarkable achievement of abstraction. And Jens Høyrup, a Danish historian of mathematics, has cited the earliest documented instance of such a representation by a length. It goes back to a cuneiform tablet of 1800 years before the Christian era, tablets of the Mesopotamian scribal school. Here a length is taken to represent something different from itself, in this case an area. And he says this is not an accident, since there are many other examples of this. And he points out, I think, a very true statement. This is one of the great steps in the history of mathematics, one of the very greatest. And whoever feels a chill when faced with intellectual progress should feel it here. This is really an extraordinary achievement that we just take for granted. Next, we come to the question which I alluded to, the treatment of time as a continuous quantity, first of all. And according to a historian of Greek mathematics, the application of the concept of continuum to time and process, again a remarkable human achievement, does not appear to have taken place before the middle of the 4th century BC. So the transfer of the concept of spatial continuum to time took place, as far as we know, in the 4th century BC, and as far as can be ascertained, it was Aristotle, in his analysis of motion in the physics, who first represented a time interval by a length. He utilized geometrical representations of both one-dimensional spatial and time intervals by length intervals in order to compare time intervals with spatial intervals, particularly in the discussion of Zeno's paradox. And you have a modern edition which shows you such diagrams. And you see time and space are represented side by side. They're not linked in a common diagram. That only comes much later, as we'll see in a moment. Archimedes used similar diagrams in the propositions 1 and 2 of his book on spirals, and here's a picture from a modern French translation of Aristotle, which had a nice picture. You see how similar it is, Archimedes, see how similar it was to Aristotle's diagram. But neither Aristotle nor Archimedes nor any of their successors for 2 millennia combined the temporal and spatial intervals into a single two-dimensional diagram, something we take for granted. The first use of time in a truly two-dimensional diagram appears to have been made by Nicolas Arém in the mid-14th century. However, he plotted time against velocity, not distance. And here again is an illustration from a modern edition of his work of translation. Now, I thought first I'd find it in Descartes, space and time put together in a diagram. No, Descartes used diagrams with points of a curve referred to two orthogonal spatial axes. So he puts two spatial axes together in his geometry. But the idea of conjoining time with space in a two-dimensional diagram did not arrive until well over half a century later, after Descartes, as we'll see in a moment. However, Descartes did offer a definition of dimension that justified the spatial representation of any quantifiable property of a system. Again, something we take for granted, but which was a conquest of thought only in the 17th century, as we see. And this is from Descartes, translated. By dimension, we understand nothing but the mode and reason according to which some subject is considered to be measurable, so that not only length, breadth, and depth are dimensions of a body, but in addition, its gravity, its weight, in other words, is a dimension in accord with which subjects are weighed. Its velocity is a dimension of motion, and an infinity of others of this type. And indeed, it's clear from his other writings that time constituted such a dimension for Descartes. But as I said, the first two-dimensional graphic representation of a spatially one-dimensional motion, plotting distance and time as orthogonal coordinates on the same diagram, was done first by Pierre Varignon near the turn of the 18th century. That's the name of the paper. Varignon actually plotted position, time, and velocity on the same diagram, that he may be said to have introduced the first phase space diagram as well. Here's the journal in which it appeared. Here's the article, and here's a modern translation with the diagram pictured. You see, he's put three things together, time, space, and velocity all plotted there on the same diagram. And Varignon realized he was doing something extraordinary, because what are you doing when you put space and time together? They're not the same thing. Aren't you putting oranges and apples together? How can you do this? Varignon considers this question, which is usually ignored today when we do these things. Space and time being heterogeneous magnitudes, it is not properly they that are compared with each other in the relation called speed, but only the homogeneous magnitudes that express them, which here are, and will always be in what follows, either two lines or two numbers, or two of any other homogeneous magnitudes that one likes. One can only put like and like in the same diagram. Varignon is quite explicit about that. D'Alembert, half a century later, is even more explicit in his treatise on dynamics, a marvelous book in many respects, as we'll see. He says, one cannot compare with each other two things of a different nature, such as space and time. But one can compare the relation of portions of time with that of the portions of space traversed. And then I'll skip part of the quote, but the next part. When one draws an equation of a curve in a space-time diagram, the equation of this curve will express not the relation of the times to the spaces, but if one may so put it, the relation that the parts of time have to their unit to that relation that the parts of space have to their unit. And the only modern textbook I've ever found that makes this point explicitly is Schouten's book on tensor analysis for physicists. But it's very important to realize that. It saves us from a sort of reification of mathematics. We realize that we suppress the dimensional differences in our mathematical diagrams, whereas, of course, physically, these are extremely important things, and we never should forget that. Euler appears to have been the first to resolve forces and motions into their components along three fixed mutually perpendicular axes. In his work on the movement of solid bodies, rigid bodies. And here's such diagrams he has where they have 3 dimensions. He was the first one to actually realize that since Euclidean space is isotropic, the 3 orthogonal axes can be chosen in many ways, and he wrote the transformation equations when you rotate from one orthogonal coordinate system to another. And here's the actual famous equations which everybody learns if they take rigid body dynamics, how you transform from one system of coordinates to a rotated system of orthogonal coordinates. At about the same time as Euler was doing this, D'Alembert first introduced the idea of time as a 4th dimension in his article on dimension in the Encyclopedia. Here's the French text, English translation. Above, I said it is not possible to conceive of more than 3 dimensions. A clever friend of my acquaintance, my guess is he's talking about himself, nevertheless believes that one may regard duration as the 4th dimension, and that the product of time by solidity would be in some way a product of 4 dimensions. The first reference I can find such an idea. Lagrange is even more explicit half a century later in his theory of analytic functions, asserting, when we look upon mechanics as a 4-dimensional geometry, and mechanical analysis, what we today call analytical mechanics, as an extension of geometrical analysis. The next interesting step, I'm skipping many things, of course, in 1887, Henri Poincaré developed a 2-dimensional 4th geometry as coherent of those as Euclid, Lobachevsky, and Riemannian. So he's talking about the geometries of homogeneous and isotropic geometries, but he developed another 4th geometry. In this geometry, the parallel postulate is preserved, so it's a flat geometry, in that sense comparable to Euclid, but the isotropy of space is abandoned, and the concept of rotation is replaced by that of pseudo-rotation. Here's a sort of diagram. You see I've given a sort of modern twist. I've given 3 different types of lines, time-like, space-like, and null. Because, although neither Poincaré nor any of his contemporaries seems to have noted this at the time, today we recognize that 2-dimensional Minkowski space-time satisfies the axioms of Poincaré's 4th geometry. In this geometry, all straight lines are not equivalent, but fall into 1 of 3 inequivalent classes. For the first 2 classes, a pseudo-rotation can bring any line to coincide with any other in the same class. But no pseudo-rotation can bring a line of one class to coincide with a line of the other. In the later Minkowski language, we would call them space-like and time-like straight lines. The third class consists of only 2 lines that separate the 2 other classes. Each remains invariant under pseudo-rotations and is therefore orthogonal to itself. And in Minkowski language, these are what we call the null lines. So Poincaré had the geometry in 1887, but neither he nor Minkowski nor anybody else until recently seems to have realized that this was 2-dimensional Minkowski space that he had formulated. And Minkowski, of course, realized that a 4-dimensional treatment of space-time is particularly suited to geometrical visualization of the transformations of special relativity. And he's the first one to use the word space-time point, for example, and rather pretentiously designated the 4-dimensional relativistic space-time as the world, die Welt, or the universe. Like Poincaré, he showed that if the temporal coordinates were made imaginary, Lorentz transformations could be interpreted geometrically as rotations in a 4-dimensional Euclidean space. But of course, it's much more common and much more fruitful today to use the real time and speak of pseudo-rotations in space-time. Poincaré should have realized that since he had actually invented that geometry, as I said. Now I'm going to backtrack and switch to a philosophical problem. So we're going back to 2 concepts of space. Historically, since at least ancient Greek times, there's been a conflict between 2 views of the nature of space, the absolute and, as you might guess, the relational. According to the absolute view, space is a container in which matter moves about. Democritus and the Greek atomists and the Roman atomists following them, Lucretius, for example, Democritus says, by convention are sweet and bitter, hot and cold, by convention is color, in truth are atoms and void. And this seems to be the origin of the distinction between primary and secondary qualities, which recurs again with Galileo so much later. And a more colorful translation you sometimes find is, nothing exists but atoms and void, all else is mere opinion. The great opponent of this point of view was Aristotle. He sort of mocks the concept of the void, what we would today call pure space. The believers in its reality presented to us as if it were some kind of receptacle or vessel, which may be regarded as full when it contains the bulk of which is capable, and empty when it does not. Aristotle espoused a relational view. Space has no independent existence. It is just a certain set of positional relations between material entities. Therefore, there cannot be a void. So Aristotle's doctrine, as has often been remarked, is really a doctrine of place rather than space. So motion is a displacement of one portion of the content of the material entities relative to another, rather than movement through space. Of course, Aristotelianism triumphed, and atomism vanished from the Western philosophical tradition for almost 2 millennia. With its revival in early modern times and subsequent adoption by Newton, the atomic point of view, the conflict between the absolute and relational concepts was renewed in the 17th and 18th centuries in the battle between Newtonianism and Cartesianism, the philosophy of René Descartes. And as usual, Voltaire has wittily summarized the situation in his letters on Newton's theories. A Frenchman who arrives in London will find philosophy, like everything else, very much changed there. He had left the world of plenum, the Cartesian point of view, and he now finds it a vacuum, the Newtonian point of view. This time it was the absolute Newtonian concept that triumphed in spite of the cogent arguments, philosophical arguments of Leibniz and Huygens against it. And again, Voltaire remarks, in fine, the better to resolve, if possible, every difficulty, he, Newton that is, proves, and even by experiments, that it is impossible there should be a plenum, and brings back the vacuum which Aristotle and Descartes had banished from the world. And Euler further emphasized that absolute space seems to be necessary if one wants to use Newtonian dynamics. He essentially says, yes, the arguments of Leibniz and Huygens are philosophically very cogent, but if you want to get on with the work and do some physics, you better take the Newtonian point of view. Now, of course, when we come to the modern point of view, we have to take these concepts of absolute relational and transfer them from the concept of space to the concept of space and time, space-time. Einstein summarized the situation as regards space in these words, and these are actually a quote from one of Einstein's last writings. Two concepts of space may be contrasted as follows. Space as positional quality of the world of material objects, space as container of all material objects. You see, it's just a renewal of the old conflict between Democritus and Aristotle. In case A, space without a material object is inconceivable. In case B, a material object can only be conceived as existing in space. Space then appears as a reality which, in a certain sense, is superior to the material world. The space can exist without the material world, the material world cannot exist without space. And this brings us to another theme which has recurred constantly in the history of philosophy, things versus processes. The old emphasis on space and time as separate favors the concept of things occupying regions of space and changing over, of course, what in the earlier times would have been the absolute time of Newtonian physics. The new emphasis on space-time favors the concept of processes occupying regions of space-time, even with the development of the field concept, all of space-time. Events are just limiting cases of processes as the region of space-time gets smaller and smaller. So now we get two concepts of space-time. The absolute one, space-time is an independent container in which processes take place. In addition to ponderable matter, such processes now would have to include fields, for example, the electromagnetic field, and as we'll see, the inertial gravitational field. The relational point of view, space-time has no independent existence. It is just a certain, just a certain set of relations between the elements of processes. And from this point of view, there could not be an empty space-time. And to anticipate, I will try to show that general relativity more or less forces us to adopt this point of view. There has been in the past, and I think today, considerable philosophical controversy over the interpretation of the space-time formalism. Is it merely a convenient mathematical tool for representing, and in its geometrical form, diagramming the spatial-temporal relations between events and processes, much like the pressure-volume-temperature diagram so useful in thermodynamics? I don't think anybody has ever tried to attribute an independent existence to a pressure-volume-temperature diagram. Or is space-time to be ontologized? Its opponents would say reified, so that space-time is primary and processes secondary. Well, as you may have guessed, I would favor the first point of view. Now we have to go into some mathematics, talk about what kind of, when we talk about space-time, we're talking about, in physics, space-time structures. There are two distinct types of space-time structures inherent in both classical and special relativistic space-time, and we'll see the fate of these in general relativity as we proceed. The chronogeometrical structure, which determines the behavior of ideal measuring rods, geometry, and clocks, chronometry, and the inertial structure, which governs the behavior of free particles, that is, those subject to no net external forces. And I'll come back to what that nota bene means in a moment. There are also compatibility conditions between the two. And I should say a word here. I'm not here advocating operationalist point of view. My point of view is not that these things are real because they're measurable, but they're measurable because they're real. I just put that into parenthesis. Now, why do I say NB? Because my point of view here differs somewhat from what you will usually find in the textbooks. In fact, it differs considerably. Usually the inertial and later the inertial gravitational structure, in terms of the connection, is derived from the chronogeometry, the pseudometric. But I maintain this is not the best way to proceed, because much recent progress in general relativity has come from emphasis on the primacy of the connection over the pseudometric. Pseudometric because of the signature, by the way. I'll often slip and just say metric. I mean the metric with the Minkowski signature. And secondly, the connection is what makes general relativity comparable to gauge theories and quantum field theory, so that emphasis on the connection has brought general relativity much closer to the rest of physics, theoretical physics community, because the comparisons between quantum field theory become much clearer when one puts more emphasis, primary emphasis, on the connection. Now I'm going to say a little bit more about each of the two structures, two types of structure, chronogeometry and inertial and then inertial gravitational structures. In both Galileo-Newtonian and special relativistic space-times, the geometry of the relative space of each inertial frame is Euclidean and can be measured with ideal measuring rods at rest in that frame, for example. Now, the distance along any spatial path depends on the path taken. The shortest distance is along the straightest path. For chronometry, however, there is a big difference between the two, between Galileo-Newtonian and special relativistic space-time. In Galileo-Newtonian space-time, the time along any time-like path is independent of the path. All ideal clocks measure this absolute and universal time. It doesn't matter what you do to the ideal clock, so long as it remains ideal, it will measure the time interval between two events, no matter what the absolute time interval between two events, no matter what path you take. In special relativistic space-time, on the other hand, the time along any time-like path depends on the path taken. Thus, time is more like space. But there's still a big difference. The longest time interval is along the straightest path. That's the twin paradox, which we heard about earlier in the conference. In classical kinematics, as we have seen, the chronometry is independent of the geometry. Time is absolute, in other words. But in special relativistic space-time, the two are united in one absolute chronogeometrical structure called the pseudometric. And here I want to take a moment to emphasize this contrast between global and local time. The Newtonian absolute time is both global and local. Global because it can be used for defining distance simultaneity in each inertial frame. And this is a very important point, a definition of distance simultaneity is always needed, and no physical result can depend on this definition. Even in Newtonian theory, it's a matter of convention that we call two events at the same absolute time simultaneous. We could adopt any other definition. No physical result can depend on a definition of distance simultaneity. But the Newtonian absolute time is also local. It provides the readings of any good clock along its world line. And the absolute time between two events is read by such clocks is independent of their paths. That's the point I want to emphasize, and the difference between Newtonian versus special relativistic time. In special relativity theory, the global and local concepts of time split apart. The global one, various definitions useful in different contexts. For example, the retarded time along the world line can be used, and this Bondi's K calculus, for example, is an excellent way of presenting special relativity, essentially based on use of retarded times. You have the same global time at any event, but different times for different world lines in this point of view, which differs from the Poincare-Einstein convention, which most people use, using light signals to synchronize, which is most useful for inertial frames, leads to different times for different inertial frames. But the point I want to emphasize is nothing physical can depend on these definitions. The local concept of time in special relativity is now the proper time along a time-like world line, as was emphasized in some of the earlier talks. It is still absolute, that is frame independent, but path dependent. Time is just more like space, as I said, but there's still that big difference. The straightest path in time is the longest. And the reason I'm emphasizing this is because of the moral I want to draw. Loose talk about space and time being relative is just that, and leads to many philosophical misinterpretations. Global space, which is in mathematical terms a vibration of space-time, and global time, which in mathematical terms is a foliation of space-time, are relative, yes, but nothing physically significant depends upon them. Local space intervals and local time intervals are absolute, but both are path-dependent. And that's the crucial difference, that space was always path-dependent, even in Newtonian Galilean space-time, but now time in special relativistic space-time is path-dependent, but absolute still. So the physically important things are absolute but path-dependent. Now, I've used the word straightest above, and I've actually been encroaching upon the domain of the second type of space-time structure, the inertial structure. This determines the motion of freely falling, that is, no net force acting on the bodies, which are called just particles for short. In both Newtonian, Galilean, and special relativistic spacetimes, such free particles follow the time-like straightest inertial paths, geodesics of space-time, straight lines for the flat spacetimes of both classical and special relativistic physics. And here, mathematically, to define things like straight, we use, therefore, to define what is called the inertial structure, all we need is the concept of an affine space. We don't need any metrical concepts, in which parallelism and the ratio of parallel lines are the meaningful concepts. The affine structure defines the concept of parallelism for two vectors at neighboring points of space-time, and the geodesic is the straightest curve in the sense that its tangent vector remains parallel to itself as it is transported along the curve. So one doesn't have to use any metrical concept to define straightest. Now, these two structures exist, and I've tried to emphasize that it's most important to define them independently of each other, for reasons we'll see more clearly in a moment. But the two structures are compatible in both Galileo-Newtonian and special relativistic spacetimes. The extremals, defined by the pseudometric, the shortest paths for space-like curves, the longest paths for time-like curves, are the same as the straightest paths defined by the inertial structure. And parallel transport of a vector, using the concept of affine parallelism, preserves the length of a vector if there is a pseudometric present. So these are among the many consequences of the compatibility conditions between the two. As I said, I'm trying to avoid mathematical equations, so I'm just giving some geometrical physical motivation for these concepts. Now we come to the concept of curvature, which is important for gravitation. Both structures, the pseudometrical and the affine inertial structure, chronogeometry and inertial structure, let's say, are flat, in the sense that for the chronogeometry, there's no Gaussian curvature associated with any of the two planes defined by the pseudometric. I'll say a bit more about this in a moment, this let me finish. For the inertial field, there is no Riemannian curvature associated with the parallel transport of vector in Newtonian, Galilean, or special relativistic spacetime. Any vector parallel transported around the closed curve coincides with itself when it comes back to its starting point. And again, the concept of curvature is often used without making a distinction between these two concepts, what I call Gaussian and Riemannian curvature. So I have to say a word about what I mean here. Gaussian curvature is connected with the question of, you have some surface, let's say. What are the radii of the circles that best fit each two-dimensional cross-section of the space? So here's a picture of a certain surface, right? You can slice that surface into two-dimensional, well, in this case, one-dimensional cross-sections, right? And you see what circle best fits each piece of the curve at a point. That's the Gaussian curvature. What's the best fitting circle for a bit of a curve that you cut this into at each point? So it has to do with dividing it up into two planes and seeing what kind of radii of curvature you get for all the various two planes. And there are, of course, compatibility conditions between the kinds of curvatures you can get, but I'm not going into mathematical detail. On the other hand, Riemannian curvature is concerned with a different question. What happens to a vector when it is transported parallel to itself around the closed curve? And here's an example that shows you what happens if you do this on a sphere. You take this vector, parallel transport it to itself along a line of longitude, I guess, longitude. Take it down here, then transport it along the equator parallel to itself, and then transfer it back up. And you see it does not come back to the original vector. That's what Riemannian curvature means. When you go around a closed loop, you do not come back, you parallel transport a vector around a closed loop, you do not come back to its original position, its original vector, then you have Riemannian curvature. So they're two rather conceptually different ideas. Now, why I've introduced the idea of curvature? Because in Newtonian gravitation, the curvature comes up. If you do a four-dimensional version of Newtonian theory. So I'm violating history here. I'm treating Newtonian theory from a modern four-dimensional point of view, first developed in the 20th century after general relativity and in response to the understanding that general relativity brought us about the importance of inertial gravitational structures. So special relativistic space-time proved sufficient for the analysis of all physical phenomena for which gravitation may be neglected. But it must be modified to include gravitation because of, our old friends we heard a lot about earlier today, because inertial and gravitational mass are equal, there is no unique way to separate the effect of inertia and gravitation on a falling body. The famous Leaning Tower of Pisa reminds you of Galileo's work. Here's the Einstein elevator, taking a ride on the Einstein elevator, accelerating upward in an inertial frame, therefore in a non-inertial frame of reference, is physically indistinguishable from being at rest in an inertial frame of reference with a uniform gravitational field. And Einstein drew remarkable consequences from that, such as the bending of a light ray in a gravitational field. If a light propagating in a straight line in an inertial frame appears to be curved in an accelerating elevator, the equivalence principle tells you that that light ray must also be curved by a gravitational field. So even at the Newtonian level, because of the fact that inertia and gravitation cannot be separated, the content of the equivalence principle mathematically is that there is an inertial gravitational field which cannot be split. Gravitation, therefore, at the four-dimensional level is not an external force acting on bodies, but a modification of the hitherto fixed and flat inertial structure of space-time, which now becomes a dynamical structure, the inertial gravitational field. While the inertial structures of both Galilean-Newtonian and special relativistic space-time are flat, the inertial gravitational structure is no longer flat. And the Riemannian curvature associated with the Newtonian inertial gravitational field describes tidal gravitational forces. Tidal forces are described mathematically by what is called the equation of geodesic deviation. You see, you are falling on a geodesic, freely falling in inertial gravitational field. You say, what are you talking about, gravitational forces? I'm just going on the straightest possible path I can. I'm going on a geodesic. But you look at your neighbors who are also freely falling. Are you accelerating toward them or away from them? Or is the distance between you just changing linearly or not changing at all? If there's any relative acceleration, tidal force, between two nearby freely falling bodies, then the total amount of such relative accelerations in various directions is a measure of the components of the Riemannian curvature tensor, which I pictured to you somewhat earlier. So this is why Riemannian curvature has to do with gravitation in the first place, because it's a direct measure of tidal forces, tidal gravitational forces. Here I've given you a picture of the tidal force of the Earth. You realize the tides are the effect of relative acceleration of different parts of the freely falling ocean on the Earth's surface. So in the presence of the Newtonian inertial gravitational curvature, the Newtonian chronogeometry remains unmodified. It's a sort of halfway house between no gravitation and general relativity. The chronogeometry remains the same, although the invariance group is enlarged, I remark parenthetically. But the two structures still remain compatible. Even when moving around in an inertial gravitational field, ideal measuring rods and clocks still correctly measure lengths and time intervals. Sometimes you see statements to the effect gravitation distorts the reading of rods and clocks. This is not the Einsteinian point of view. The Einsteinian point of view is that rods and clocks, even in an inertial gravitational field, ideal rods and clocks will read proper time and proper lengths. And in Newtonian theory, this is certainly true as well. Now we come to general relativity. Special relativistic chronogeometry, on the other hand, is not compatible with a non-flat inertial gravitational field. So at Newtonian level, even though you introduce gravitation as an inertial gravitational field, a connection, it's still compatible with the flat chronometry and geometry separately. But once you go to general relativity, and once you go to the special relativistic level, the chronogeometry of special relativity is not compatible with non-flat inertial gravitational fields. So you have two choices. You give up the compatibility and you develop the special relativistic theories of gravitation. But Einstein's course was quite the reverse. Restore compatibility by dynamizing the chronogeometry. The pseudometric now becomes a non-flat dynamical field that plays a dual role in physics. In addition to still determining the chronogeometry, it also serves as the potentials that uniquely determine the inertial gravitational field. And this is why people get away with not even talking about the inertial gravitational field independently. But I think, as I said before, it's much more advantageous to treat the two as separate and then realize that there are compatibility conditions that make the two so closely related. So now let's contrast the situation as far as absolute versus relational points of view go, the pre-general relativistic situation and the relativistic situation. For both Galilean-Newtonian and special relativistic spacetimes, it was possible to hold either the absolute or relational viewpoint, although there were serious problems for the relational viewpoint. The existence of regions of space-time that are empty of matter and fields. If there are empty regions of space-time, how can the properties of space-time be determined by the contents of space-time? Difficult question to answer. Then the fact that the space-time structures remain the same regardless of the varying physical processes taking place within them. Why do you always have Euclidean geometry, for example, if geometry is a result of the material processes going on? Why don't different material processes produce different geometries? Again, a problem for the relational point of view. And the fact that space-time structures influence physical processes, but are not influenced by them. The law of inertia, for example, influences all physical processes, but physical processes do not affect the law of inertia in pre-general relativistic situations. In these cases, we speak of these chronogeometrical and inertial structures of the pre-general relativistic theories as fixed background space-time structures. In these theories, we have kinematics first and then dynamics. One can have a kinematics that is independent of the dynamics. These fixed backgrounds are essential features of quantum theory. It's important to point out. For non-relativistic quantum mechanics, the Galilean-Newtonian space-time is the background structure, fixed given background structure. For relativistic quantum field theory, special relativistic space-time is the fixed given background space-time structure. And anyone who works in the field and thinks about it for a minute understands this completely. I refer you a recent review article, which is written from a philosophical point of view, but Dosh is one of the old-time experts in quantum field theory, so he knows quite well what he's speaking about. And he points out the basic concepts of the theory are quantum fields defined on space-time, not particles. Space-time is assumed to be a four-dimensional real vector space with given metrical properties and Einstein causality, such that the Poincare group, constituted by translations and Lorentz transformations, is implied as a symmetry group. This space-time structure, fixed in advance, called Minkowski space, forms the register for recording the physical events. And I want to emphasize this, there's a twofold role that space-time plays. First of all, you see it's a fixed background. He starts out by telling you that. It forms the register for recording physical events. The basic purpose of quantum theory, and any kind of quantum theory, is to predict the probability amplitude for some process. Well, how do you test the probability amplitude for a process? Well, you put the piece of apparatus which produces the process at one place, and start process at some time, and you have another piece of apparatus someplace else which registers the results of the process, and you therefore see whether the probabilities you predict for the various positions of the results agrees with the theoretical predictions or not. But how do you know where to place your apparatus? And how do you know when to open your gates or start your counter clicking? You see you're in a fixed background space-time. So you use the fixed background space-time not only for the theory, the quantum fields in terms of which theory are constructed, are operated as dependent on space-time. So the space-time is not only used for the theory, but it's used for the measurement processes as well, the fixed background. So it's absolutely crucial to both the formulation of the theory and its physical interpretation. That's quantum theory either at the non-relativistic or the special relativistic quantum field theory level. Now we come to the general relativistic revolution. With the advent of the general relativistic space-time structures, the problems for the relational viewpoint disappear, first of all. Remember, the first problem was empty regions. There are no empty regions of space-time. Wherever there is space-time, there is at least an inertial gravitational field. So you cannot have space-time without having an inertial gravitational field. The space-time structures, remember originally we said, why is the space-time structure independent of the processes going on in it? It's not anymore. Space-time structures are not independent of processes taking place within them. They are dynamical fields. The space-time structures are now all dynamical fields, obeying field equations, relating them to all other physical processes. And that takes care of the third problem, too, why the action only goes one way. There are now reciprocal interactions between space-time and other physical processes. In fact, the Einstein field equations are usually coupled with some other equations because somebody mentioned this morning that the stress energy tensor tells the geometry how to curve. It's not quite correct because almost all cases the stress energy tensor itself contains the metric. If you want to write down the stress energy tensor, you have to know the metric. So you're really dealing with a coupled set of equations for the matter field and the metric. The space-time. The matter is not telling the space-time how to curve and so forth because they're coupled too intimately for that simple picture to work. So now in the case of general relativity, we speak about a background-free theory. We speak of general relativity as a background-free theory in which kinematics and dynamics can no longer be separated. There is no kinematics before dynamics. So the slogan is, no kinematics without dynamics. That's the one lesson. If you take anything away from the talk, take that lesson away. Now, general relativity more or less forces one to adopt the relational viewpoint. And this is a long quote from Einstein, again, one of his last writings. On the basis of the general theory of relativity, space, as opposed to what fills space, has no separate existence. If we imagine the gravitational field to be removed, there does not remain a space-time of the type of Minkowski space-time, which often you see that statement that empty space-time is what happens to take matter away. But in Einstein's vision, absolutely nothing remains, not even a topological space. And in more mathematical treatments, recently with a collaborator, we've shown how to realize Einstein's vision by using fiber bundle language rather than just starting out with a bare manifold. So this ideal can be realized quite well for general relativity. But I want to emphasize the last point. There is no such thing as an empty space. That is a space without field. He means space-time, of course, when he says space. Space-time does not claim existence on its own, but only as a structural quality of the field. Now we come to the problem of quantum gravity, which essentially can be boiled down to this: how to invent. Einstein preferred the word invention over creation or discovery, and I haven't got time to say why, but I think it's a good choice of words. How to invent a theory that will encompass both quantum field theory, which as we're seeing is highly background dependent, and general relativity, which is background independent. And the answer is nobody so far has succeeded in doing it, and there are many, many suggestions, but we're far from having reached that ideal. Now, quantizing general relativity. As early as 1916, Einstein realized that general relativity would require a quantum version. He did the sort of gravitational version of the Bohr atom. If you have two bodies circling each other gravitationally, they should radiate. He just discovered gravity. He just written his paper about gravitational radiation, and the radiation should soon cause the system to collapse. Well, just as that doesn't happen in the Bohr atom, he assumed it would not happen for a gravitational system. Therefore, it must be there's some quantum conditions which prevent that from happening. But the first serious attempts to apply the methods of quantum field theory to general relativity came in the 1930s, inspired largely by Pauli and done by people who were either his students or had worked with him, and was first carried out in detail by Leon Rosenfeld. Here's a picture of young Leon Rosenfeld. But the basic philosophy behind the work of Rosenfeld and the Pauli school was only technical difficulties, nonlinearity basically, stand in the way of application of the methods of quantum field theory that were to prove so successful, for example, in quantum electrodynamics. In the 1930s, only one physicist realized that they were profound conceptual problems, and that is Matvei Petrovich Bronstein, whom I named the Bronstein cube after. He was, at that time in the 30s, the only real contender against Lev Davidovich Landau for leadership of Soviet theoretical physics, the only one that could be spoken of in the same breath with Landau. Both were imprisoned during the Stalinist purges. Landau survived, thank goodness. Bronstein perished. And I really think the history of post-World War II development of quantum gravity might have been different had Bronstein lived. Just a quote from his papers to see, from 1936, his fundamental paper on quantization, even in the weak field limit, he essentially realized that there's a big difference between quantum electrodynamics, as discussed by Bohr-Rosenfeld measurement of quantum electric and magnetic fields, and the gravitational field. I don't have time to go into it, but I just want to point out, he says, the elimination of the logical inconsistencies connected with this require a radical reconstruction of the theory, and in particular, the rejection of a Riemannian geometry, dealing, as we see here, with values unobservable in principle, and perhaps also the rejection of our ordinary concepts of space and time, modifying them by so much deeper and non-evident concepts. Ves nicht glaubt, bezahlt, and Antala. That's a quote from one of the Grimm brothers' fairy tales. But you see how strongly Bronstein presented the case. Now, I have no time to say any more about the history of quantum gravity, but it's important to note that the conflict between those who see only technical problems in the application of existing techniques of quantum field theory and those who see profound conceptual issues started as early as the 1930s, at the beginning of the serious work on quantum gravity, and it continues to this day. There are two schools of people who work on the problem of quantum gravity. People who work on the quantum field theory point of view say, well, we have to keep background space-time of however many dimensions. They don't restrict those to 4, but they do keep a background space-time, and somehow incorporate general relativity, even if you have to modify it. For example, supersymmetries, et cetera, et cetera. And the current strongest candidate for that is string theory. And here I go back to the Bronstein cube. Now you know who Bronstein is. You start from Galileo-Newtonian theory, you go up to non-relativistic quantum mechanics, then you go to quantum field theory, and you try to reach the promised land of quantum gravity in this direction. You come to something like string theory as the strongest candidate so far, membranes, whatever, string theory in short for this whole approach. Those who start from the general relativity point of view are working on the opposite point of view. Let's see if we can't develop a background independent formulation of quantum theory and apply it to the field equation of general relativity. And here the current strongest candidate is loop quantum gravity. And again, you see this box diagram doesn't commute. If you go from Galileo-Newtonian theory to special relativity, then to general relativity, and try to go up here, loop quantum gravity is the current best candidate for this approach. So it depends which direction you take. As the mathematicians say, this diagram does not commute. And again, I can't go into any detail about the mathematical issues involved, but I do want to emphasize the importance of the inertial gravitational connection. In contrast to previous approaches such as geometric dynamics, which took the metric as primary, the important achievements of loop quantum gravity are based on taking the connection as primary. And this is essentially the Ashtekar variables, if people know anything about that. But I just want to emphasize the importance of the connection. Now, I'm not implying by this that either of these approaches has been fully successful. In fact, none of the current approaches has been completely successful in solving the problems of quantum gravity. That's a mild statement of the case. There are crying problems in each approach. Well, this suggested to me that we look for a new formal principle. Remember what Einstein says in his autobiographical notes. In 1905, he despaired of finding a constructive theory of matter and radiation, so he started to look for a new formal principle that could guide him in the search. And that's how he arrived at the theory of special relativity, as what he called the theory of principle, sort of traffic rules for playing the game in the future rather than a constructive theory itself. So I have been led to propose a new formal principle that might serve as a guide in the further quest, whatever direction it may take, for a quantum theory of gravity or whatever else, other direction theoretical physics may take. And I call this section from general covariance to permutation invariance. I'll talk a little bit about the principle of maximum permutability, space-time points, identical particles, quantum statistics, and quantum gravity, what are the basic entities. But before I go into that, I want to emphasize that this point of view I'm emphasizing does not exclude string theory. I'm not arguing against string theory. I'm arguing that if one is going to develop string theory, one should develop a background-independent version of string theory. And this is what string theorist Brian Greene has recently emphasized. He's presented an appealing vision of what string theory without a background space-time might look like. But he has also emphasized how far string theorists still are from realizing this vision. And that's his recent popular book. He says maybe space-time is stitched out of strings, much as a shirt is stitched out of thread. And as yet, no one has turned these words into a precise mathematical statement. As far as I can tell, the obstacles to do so are far from trifling. Again, that's a mild statement of the issue. And he says, we picture strings as vibrating in space and through time, but without the space-time fabric that the strings are themselves imagined to yield through their orderly union, there is no space or time. And skipping to the italicized portion, to make sense of this proposal, we will need a framework for describing strings that does not assume from the get-go that they are vibrating in a pre-existing space-time, which is the main work so far in string theory. We would need a fully spaceless and timeless formulation of string theory in which space-time emerges from the collective behavior of strings. A worthy ideal. I just want to show you that so you don't accuse me of being anti-string theory. The best string theorists are well aware of the issue. Although there has been progress toward this goal, no one has yet come up with such a spaceless and timeless formulation of string theory, again, quoting Brian Greene. And he says, many researchers consider the development of a background-independent formulation to be the single greatest unresolved problem facing string theory. Well, back to my suggestion, which I offer modestly, but just so that you don't say, well, what should we do? I have at least an idea about how one might do, what one might do, to have a basic formal principle, as I say, to guide one. Diffeomorphisms in general relativity are just highfalutin permutations, automorphisms of homogeneous elements of space-time. And to make that sense out of that statement, I have to explain the difference between algebra and geometry. And here I'm using the work of Weil to define what a geometry is, and who summarizes the experience of a century, and Shafarevich to define what an algebra is. A geometry is a set of elements together with some relations between them. All the elements are homogeneous under some group of automorphisms, permutations. These are more or less synonymous words that preserve all the relations. For example, what is Euclidean geometry? The Euclidean plane, the elements of which are all, the points of which are all homogeneous, no distinction between them, and the group of translations and rotations is what defines Euclidean geometry. So you say whatever is invariant under the group of translations and rotations is Euclidean geometry. This essentially goes back to Klein's work on definition of geometry. So one may speak here, and I have in some of my papers, about things between relations. The relations are primary, and the things, the elements of the space, are secondary. So the things between relations contrasted with algebra, which you have a set of elements together with some relations between them. All the elements are individuated independently of the relations. That's the difference. So in this case, you can speak of the relations between things. The things are primary and the relations are secondary. For example, the rotation group. A rotation, the identity rotation, or a pi rotation, or a pi over 2 rotation are quite uniquely defined things. So each element of the rotation group is uniquely defined. It's individuated independently of the relation between the rotation. So that's the difference between a geometry and an algebra. But there is a close relation between the two, which often leads to a blurring. One often uses a coordinatization, a representation of an abstract space, algebraic if it's characterized as a space by means of the coordination of its points, which we often do. So coordination is a one-to-one correspondence between the elements of an algebra and a geometry. And then you have to get rid of that coordination, because if the elements of the space are really homogeneous, by coordinatizing them, you've made them appear different. So you have to say, well, they're really invariant under all possible recoordinatizations. But I want to emphasize the difference between redescriptions of the coordinate system and active permutations of the points of the space, or space-time, as we'll see. And it's the active interpretation I'm really talking about here, so we can forget about the representations. Here I just tell you the people, I got these are not my brainstorms, these are the ideas essentially of Weil and Shafarevich. Now, in a background-independent theory, there are no non-dynamical relations to be preserved in the geometry of space-time. So in general relativity, the background-independent theory, what do you have to preserve under the permutations of the elements of space-time? What does the geometry have to preserve? Nothing. Okay, if there are no such relations, then all possible permutations of the points of space-time are permissible. The demand that these permutations be continuous and differentiable, which we need for various mathematical reasons in general relativity, and you demand that, you have what we call diffeomorphisms. So diffeomorphisms are just continuous differentiable permutations. That's why I called highfalutin permutations. Highfalutin is the English word, colloquial word for fancy. The points of space-time have no inherent properties that individuate them. A background-independent theory, in other words, is the things between relations theory. The relations are primary, the things are secondary. This idea, as I showed in a more detailed mathematical paper, can be generalized from metric tensor to arbitrary geometrical objects, so one can enlarge the scope of the idea. And I owe these definitions of generalization and abstraction to Saunders Mac Lane, to whom I pay tribute. He just died this year, one of the great mathematical minds of the last and beginning of this century, one of the founders of category theory, and a really truly remarkable person. And also one can abstract. We can go from differentiable manifolds, which works in general relativity, to topological manifolds, but dropping differentiability, and even from topological manifolds to sets. So one can take this idea of permutation invariance and apply it to any kind of geometrical object and even to sets, discrete entities. So my proposal is, in the future, we don't know what direction physics will take, but it's, well, I forgot to say one thing. This idea that the elements of the structure are individuated only by their properties is just as true in quantum field theory for the field quanta as it is for the points of space-time. The whole point of Fermi-Dirac and Bose-Einstein statistics is the field quanta are all homogeneous. There is no distinction between them. If you have, for example, a certain Fock state space, you have 7 quanta in a certain state of momentum. You don't say which 7. There are 7. There is no distinction between them. They are only individuated by the relationships they have. For example, they might be emitted by a certain source of electrons, or they might be absorbed by another source, so that they're only individuated by the relationships in which you place them in an experimental situation, what Bohr calls a phenomenon and what Feynman calls a process. So my basic thought is, if the basic entities of quantum field theory have no individuation apart from the relational structure which they're embedded, and if the points of space-time have no individuation apart from the structures which they're embedded, it seems hard to believe that if we go into the future, even if the concepts of space-time and space-time have to be greatly modified or themselves explained in terms of some more fundamental entities, it's hard to believe that we would have to return from the relational to the absolute point of view, that somehow the elements would assume individuation as one got deeper and deeper into the foundations of physics. So I've been led to conjecture that whatever form a future fundamental physical theory, such as a quantum gravity or whatever else direction physics may take, there will be no absolute element in it. Rather, its basic elements will be embedded in a relational structure. It will be a truly background-independent physics. And I believe that's the core of Einstein's dream, the unified field theory dream. If you really analyze this towards, that is the unique feature about it. In that sense, if I am right, Einstein's greatest dream will have come true. Thank you.